Welcome to the fifth video from this software engineering series. Today we will talk about how to overcome hurdles by transmogrifying a problem. More specifically, we will introduce the primal dual paradigm. Sometimes the solution is seemingly unreachable by looking at the original problem description. It may be due to complex relationships between entities, inefficient algorithms, and non-convergence of the primary space. Instead of trying to combat all the hurdles in this original domain, it is worthwhile to think about whether transforming it could help eliminate those obstacles. In this video, you will learn about one powerful technique dubbed as the primal dual paradigm. The name may sound familiar to those who know about the simplex linear programming method. Nonetheless, the basic idea can be expanded and applied in a much broader context. We will showcase this with a concrete task. As a side note, recommender systems usually use singular value decomposition, which is another great example of a transformed space. The table of contents is as follows. We will first describe our use case to have something concrete to work with. Then we will introduce the structure of a solution revolving around the primal dual paradigm. Lastly, we will implement our problem from step 1. We will solve the following problem using C++11. Štale, which on Serbian means barns. This problem is hosted on the site called Petlja and appeared this year at a regional level competition for high school students. Petlja is a Serbian site dedicated to promote computer science mostly for middle and high school students. It also hosts a platform to run competitions. This site offers valuable content in English too. The link from this presentation points to this English version. Here is the text of the problem description. You would like to visit all barns, represented as points in a 2D coordinate system, by riding your horse. A horse may move from point xy to x plus a times c, y plus b times c. In other words, your horse may move along a segment horizontally, vertically, and diagonally c steps at a time. Any barn along this segment, including the endpoints, are treated as visited. Your task is to report how many barns can be visited in this manner, starting from any existing barn. You may visit some barn multiple times and you don't need to find the shortest path. The number of barns is less than or equal to 200,000. Let's look at some example test cases with c equals 3 and c equals 4 for these barns as depicted here with dots. With c equals 3, we can visit all barns irrespectively of the starting point. So if we start from here, and we are first taking c equals 3, we can move down 3 steps, and again, since we have started from here, this barn is visited already, and because this barn is with coordinates 0, 0 is along the segment from this point up to this point, we have already visited this as well. Then we can go diagonally up to here, because this is 3 and this is also 3. What we can do now is move horizontally here and finally move here, and we have reached this last barn as well. With c equals 4, we can only visit 3 barns, irrespectively of the starting point. Let's start again from this barn here. We can move down 4 steps, then again, so this is visited. Then we can move diagonally up move left, and now whatever we do, we will never be able to reach this barn. And the same story is true if we try to start from some other barn. We will be able to reach 3 of them, but the last one will be unreachable. We will solve our problem using the primal dual paradigm. This slide shows the structure of a primal dual system. In the upper part you have a primal domain, and in the lower one you have the dual domain. Both these domains try to solve the same problem, although differently. The line in the middle delineates the 2 domains. This paradigm was published in my book Unraveling Software Maintenance and Evolution, and this picture is taken from this book. If we cannot move inside the primal domain, then we can transform the primal problem into the dual problem. Once we get the dual solution, then we apply an inverse transform to reach the primal solution. Sometimes these 2 solution spaces overlap, and this will be the case in our problem as well. I will use this playground for exploring the problem. Assume that C is equal to 3, and we have these barns depicted with dots on this diagram. Our starting position will be this barn with coordinates x and y. Let me denote n as the number of barns. A general scheme how to solve this problem is easy to figure out. We would start from each barn, or more precisely, take a starting position as our pivot element, and figure out how many barns can be reached from this starting point. Then we would choose another barn and do the same calculation and maintain the maximum visitable barns as our variable and update it along this process. Finally, we would dump that variable as our solution. A brute force approach would examine each pair of barns from a starting position to some other barn. For example, in our case, this would mean we would examine this pair, this pair, this pair, and so on. This brute force algorithm would have a runtime complexity of O of n squared, and this is very slow, taking into account the size of n. So our goal is now to figure out, is there some very clever way how we can speed up the calculation of the number of barns visitable from each starting position. Let's come up with a better scheme how to calculate the number of visitable barns from each starting position. Apparently, any barn on this vertical line can be visited, because we can just move up or down as many steps as we would like. But the same is true if we move C steps to the right. Any barn on this vertical line is visitable as well as if we move left. Of course, we can repeat the same thing again, and if we would draw a vertical line here, everything on this vertical line would be visitable as well. Analogously, we can do the same for horizontal lines. This horizontal line, or any barns on this horizontal line, are visitable, and if we move up, then this horizontal line is reachable, as well as if we move down this one. Let's find some commonalities between the coordinates of all these barns visitable from our starting position situated on these vertical and horizontal lines. We have seen that from xy we can visit any other barn with coordinates x plus k times c and y plus l times c, where k and l are integers. They can be positive, negative, or 0. So we know that this barn is related to all the other barns because they are visitable. And the way how we can relate these barns is by relating their component coordinates. So I will write them down side by side. We can see that x is congruent to x plus k times c mod c, and y is congruent to y plus l times c mod c. These relationships allow us now to considerably compress the original problem space. In that space, xy coordinates are taking values from a huge interval. But now in this compressed space, this interval is much smaller. This is the primal domain, and this is our dual domain. The question is now how we may use this dual domain to count up the number of visitable barns. It turns out that this is rather trivial now. We would just need to calculate the cardinality of each congruency class, identified by xc, yc pair. In other words, we would need to introduce a 2D array of integer counters of dimensionality c by c. And for each input xi, yi, we would increment the associated counter at coordinates xi mod c and yi mod c. Let's name this 2D array as num barns. If we go back to our original diagram, let's use these num barns to calculate how many barns are reachable that are situated on these vertical lines. It turns out that what we need to do is sum up. So we would have I goes from 0 to c minus 1 of num barns xc of y, where xc is equal x mod c. And analogously, the number of barns that are reachable from the starting position and are located on those horizontal lines would be sum of I goes to 0 from c minus 1 num barns of I yc, where yc is equal y mod c. The only thing that you need to be careful is to avoid double counting the barns which happen to have, in this case, xc equal to I. So you should not count, or you should skip all the entries where I equals to xc. So this should be skipped. And let me show you on the diagram. For example, this guy. This guy is both sitting on this vertical line as well as on this horizontal line. And not only this guy, but all the other guys that would be mapped to this same xc coordinate. The only missing detail is related to these diagonal bars. Since we are using modular arithmetic, these bars here from this segment are going to be mapped to the same base segment as these guys here, or these guys. So essentially it's enough to count up the bars looking at this reference segment, which I'm going to draw here. This is XC, YC. This is XC, YC minus C. This is XC plus C, YC minus C. And this is XC plus C, YC. And these are our bars. And this coordinate is going to be, for example, XC plus 1, YC minus 1. This one is having coordinates XC plus C minus 1 and coordinates minus C plus 1. So by counting up these bars from this base segment, we will encompass all other segments as well. And this is again just another loop over the numbars array. Again, you need to watch out not to double count things. That may happen if you would have a bar here, and this intersection of the diagonals would also be situated on one of these lines. Okay, so let me show you how the code is executing. Here is how you can compile the code, and there is a small shell script for invoking the tests. Inside the tests folder you have data files, and these data files are formatted as input, out expected output, and this is the test number. And these test cases have been reused from the archive that you can download by visiting the link from this presentation. Let me run the tests. And all of them should pass. Okay, and here is the source code. The code is essentially following our design. There are two details that I would like to emphasize here. One is this function mod to properly calculate n mod m. And the other one is a remark about the asymptotic behavior of this code. This version of the code has a runtime complexity of O n plus c on cube and a memory complexity of c squared. Now, this inner loop can be removed by introducing additional one-dimensional, two-dimensional, and three-dimensional arrays, and that variant of the code, which again you can look it up by downloading the previously mentioned archive, has a runtime complexity of O(n) plus c squared, but a memory complexity of c cubed. Since c is much less than n, of course both these variants are satisfying the time limit and memory limit constraints for this problem. What can we conclude from this video? Optimization problems can be often solved in terms of a transformed problem, and this is the essence of this primal dual paradigm. The primal dual technique should be part of your algorithm design toolbox. Thinking outside of the box is equally important as deep technical knowledge. Thank you for watching this video. I hope that you have liked the content. Please don't forget to subscribe. Subscription on YouTube is free, and by being subscribed, you won't miss any future episodes.